So let me just do a quick review on that for a second there. Reminding you that problem 1 of homework 6 is Ni11 over N1, where N1 is equal to N11 plus N21. Okay, so that's going to be, I believe, is a function of temperature. Okay. Problem 2, hydrogen, helium, and calcium in your gas, for which I'm going to give you a pressure total, or gas pressure. It's meant to be gas pressure, and I do believe the other thing I give you is T. Fixed T, fixed gas pressure. Okay, and from there, the gas pressure is going to let you figure out what the total number density is. Okay, and I give you the mass fractions. So somehow between the mass fractions and the total density, okay, because the T and the G, okay, you have to solve the transcendental equation for Ne. And if you remember, that equation is I'm going to put that now. I do believe I've got that right. Yes. So this is a transcendental equation for N sub E. Okay. The alpha K you can calculate from the mass fractions. The J minus, okay, the F sub JK, you now know you have to use recursive Saha to get those. But those, if you remember right, are a function of electron density and temperature. Right. Because the Saha equation is used recursively to get these ionization fractions, and the Saha equation depends upon the electron density and the temperature. So you're really in a chicken before the egg. This depends upon the electron density at that temperature. This depends upon the composition of the gas. Here's Ne, and here's Ne. So you got Ne is equal to some Ne times some function, which is summed over all the elements for their ionization conditions, which are a function of Ne itself, which is what you're trying to solve for. Okay. Now, what I'm going to do is suggest you use something called Brent's method. Okay? Let's say you have a gas for which you want to solve this equation. Okay. So what you do is you say Ne minus this whole thing. Well, let's do this. Let's just call this some variable, okay? Capital F of NET, okay? And also alpha, apparent. So what we're going to do is we're going to say, let's calculate this for some NE and do this. Let's solve this equation, okay? So basically what you're going to do is you're going to guess at Ne, okay? And after you guess at Ne, you're going to plug Ne into this equation and calculate f of NET. You see what I'm saying? You're going to guess at Ne, so you can calculate all of the ionization fractions at that temperature for that Ne. You're going to do the summation You're going to then multiply by n minus the NE you guessed, where n is the total, and then you're going to see, does that equal the NE that I guessed? This function is going to look something like this. I don't know what to call it. No. Anybody? Call it G of NE at fixed t. At that t, you're going to have G of NE. What you want to do is you want to find out where it equals 0. Okay? So here's 0, here's positive, here's minus. And you might find that the NE that gives you the 0 is here. The axis here is NE, right? The axis is NE. And you might find that this is the NE that gives you a 0. So the function might look something like this. Okay? So you're going to start with NE low as a guess, which we'll call NEL, and you'll guess NE high. Okay. So the way you do this is you're going to first bracket where does this thing happen, and it's very simple. You're going to use something called Brent's method, and this is in Python it's called zbrent, in Fortran it's called zbrent, in C it's called zbrent. I've given you copies of the Fortran and C codes if you want to use those, but you can find them. I know people that have found them instantly in Python. And basically, you're going to calculate, say, I'm going to guess in some low NE. I'm going to lowball my guess for NE. I could call it 0 if I want. Okay. And I'm going to calculate for NE equals some small number. I'm going to calculate all these F's from the Saha equation. And then I'm going to do this sum. Then I'm going to do the second sum. And then I'm going to calculate, this is my guess NE that I put in to calculate these. I'm going to calculate this. Then I'm going to subtract it from my guess. That's going to be this, and I'm going to get a number like minus 10 to the 5. Down here. Okay. Whoops. And then I'm going to guess a big NE. Okay, well, there's only so many electrons in the gas. You could assume the gas is fully ionized to get an estimate for what the maximum NE could be at that temperature. So you do that, and you put it in here. Here's my max NE. I calculate all my ionization fractions. I do my sums. I take NE minus my guess NE. Okay, I calculate that function. I subtract it off there. I get plus 10 to the 10. Okay. Now I'm happy. Why am I happy? Because in my lower guess, I got a negative answer, and for my upper guess, I got a positive answer. So what do I know? I've bracketed the 0 point. Okay? Then so actually what happens with the zbrent code is you don't have to do any of that work. You don't have to, it'll do that for you. Okay? What you're going to do is you're going to pass the zbrent code, Brent's method, your lower guess and your upper guess, and you're going to have it call this function. So it's going to automatically start by checking that and that. Okay? And then it's going to automatically kick in to go find the root mode. All you have to give it is the lower and the upper NE and let it call this function. And it's going to then go into root finding mode for you. What's it going to do? It's going to say, well, which one of these is closer to the 0? That one's only 10 to the 5 off. I'm going to go halfway between here and there, which is there. Okay? Then it's going to calculate the value there. Okay, it's still negative, and that's still positive. So then it's going to go up and say, okay, now I'm going to go halfway between here and here. Boom. Going to calculate that. It's going to go, okay, this one's more far away, so I'm going to go halfway in between here. It calculates it there. And then it says, okay, I'm going to bring this one over here. Whoops, that doesn't work. I'm going to bring this one over here. and then calculate that. Then I'm going to bring this one over here halfway, calculate that. Oh, we're starting to get close now, aren't we? Right? We're starting to bracket that puppy. Okay. Anyway, it figures out the algorithm. It pushes these two things in here until it goes, lo and behold, I got it to come out to 0, and it sends you back the electron density for which that is a zeroed out equation. And lo and behold, this iterative method now has given you the electron density that solves. What did this come from? This came from charge density conservation, if you remember. The principle of charge density conservation is now met. Okay? Once you have NE from this, the actual NE that gives you the 0, you plug it into here. Now you can solve for NN. Now you've got NN. This came from the pressure over here that I gave you originally. This is NE from this charge density conservation. Now that you've got NN, and you've got all of the ionization fractions now, don't you? Because you found the right electron density. So your code is automatically already calculated and stored all of these. You've got all those ionization fractions, so guess what? You solved the gas. So now with NN, you can take your alphas and you can say N of K equals alpha K NN. And now that you've got your N sub K, you can say N of, 1K equals F of 1K times NK, etc., etc., etc. with your J's. And you can solve for every density of every particle from solving charge density conservation. A lot more complicated than the first homework set, right? Okay. So your key is that you are going to write a code that did what you did for iron before, but now you're going to have it do it for 3 elements, hydrogen, helium, and calcium. And you are going to use the equilibrium value based upon knowing the pressure of the gas and the temperature, okay? And then apply, this is going to be your overriding function that you want to solve. And once you've solved it, it returns NE for the equilibrium of that gas. And boom, you can unfold everything from there. Okay. That's at a fixed temperature and a fixed pressure. Okay. So if you solve this, you are like 85% of the way to solving the planetary atmosphere. Okay. Then problem 3, oh, by the way, I'm giving you the solutions to this. Okay? This is a tricky enough problem and one that you might need to spend enough time on, so I do suggest you make sure you know how to get problem 3 right from homework 5, and then I would set out to read about how ZBrint works. It's not going to take you long. That's not going to be the hard part. It's going to be keeping track of everything. Okay? And then what you want to solve for this problem, and then you want to check the solutions that I give you to make sure you got all the ionization fractions right, to make sure you got the densities of everything right, and the the molecular weights and things like that. And once you've convinced yourself you've done that, you basically have your toolbox to step out into doing the stellar model. All right. Okay. Problem 3 on this homework is basically, once you get problem 2 done, you're just going to put a temperature loop around problem 2. I give you a temperature, I believe, of 6,000 degrees here. I can't remember. I think a very cool temperature, because the reason is because calcium ionizes at a very cool temperature. It ionizes more than even hydrogen does, so it becomes the main contributor of electrons at low temperatures. Then I'm in problem 3, I'm going to have you crank up the temperature and go all the way from, I think, something like 3,000 degrees or something up to 20. I can't remember the numbers. And I'm going to have you plot what the densities are doing as a function of temperature, all for a fixed pressure. So the pressure is going to stay the same. Now I'm going to say, now just put a temperature loop around it and give me a plot of the ionization fractions as a function of temperature. Give me a plot of the number density as a function of temperature, so that you can now see how things change and behave as the temperature increases. I've asked you to please try to make plots that are as close to, journal style as possible. I want you to practice that. I think it's very important to practice how to communicate that information.
Hey Chris.
Yes,
Do
ma'am.
you care what the, the temperature step is for that? Or imagine something too small.
Did I not state it?
Oh, I haven't actually looked at that.
I can't remember if I stated it.
Okay.
But you're going from 3,000 to 20,000. Something small enough. I mean, it's a computer code, so something small enough to make your curve smooth. You should shoot for having smooth curves.
Mm-hmm.
Yeah.
But it doesn't have to be like 0.1.
No.
Okay.
No, I would 50 degrees. I'm guessing 50 degrees, 25 degrees, something like that. Okay. It could be once you get up to the high temperatures of 15,000 and above, like going in steps of 100 would be fine. But again, it's just computer code. There's no storage issues really for a code this size. Okay, so right. Any questions? All right, so I'm just going to iterate again. This is why spending time getting problem 3 right from homework 5 is important. Yes, sir.
Is Z-Brent specifically electron charge density conservation, or is it any sort of transcendental equation?
Any equation you want to throw at it. It's a tool called, just like the Newton-Raphson method. Okay.
Yeah,
you
just
could use
like that.
Yes, you know what the Newton-Raphson
No.
method. Okay. So the Newton-Raphson method is another way also of finding the zero of a equation. Okay, when you have, say, a transcendental equation, or say you have a cubic equation that you want to find the zero of. With the Newton-Raphson method, you actually take the derivatives of the equation, and then you have to program in the derivatives and do finite differencing, and so. But the problem with this is good luck calculating the derivative of that. Okay, so using a method to find the zero where you have to actually do some calculus to get the derivative. It's better just to do the brute force bracketing method. And in fact, Newton-Raphson, it can go unstable. And the first time I tried to solve this, I had to do this atmosphere problem when I was in grad school too. And the first time I had to solve for charge density like this, I used the Newton-Raphson method, where I did a numerical thing to get the derivative, and it went unstable like this. And I just kept flopping back and forth, my electron density flopping back and forth between the equilibrium value. Like, what? So then I talked to another graduate student, because my professors didn't teach me any of this. They said, just go do it, right? So I went and talked to another student who had been a computer coder professionally before he came to grad school, so he was a super hot shot. He said, oh yeah, have you heard of Brent's method? No, boom, done. It was that fast. I mean, it was amazing. This is very stable. I recommend it. So I think we were up there, Jody, we were up there talking to Jacob, and he said, oh yeah, that's a good tool to, he was saying that was one of his favorite tools that he learned in classes was this method here. So it can be something that will be useful for you in many walks of life. It's not just electron density conservation. It's a general canned routine. If you want a good description of it, you can Google it. There's probably some good descriptions of it. And how many people have looked at that book called Numerical Recipes? Okay, they talk about Brent's method in Numerical Recipes, a couple pages, usually pretty short and sweet in that book. Good method. Okay. So once you solve this homework problem, what's left is the atmosphere. And when we meet next, I'll pass out that. Now the difference between problem 3 and the atmosphere is that both your pressure and your temperature are going to change as you move down the atmosphere. And what's going to constrain that curve of pressure and temperature is going to be the hydrostatic equilibrium. And so that brings us back to the pressure gradient and the temperature gradient that we talked about last time. And that's why I'm sort of talking about those now. And then what we're going to do is make the last connection. Once we finish temperature gradient, we know what the pressure gradient is. That's very simple, dP dr equals minus g rho. We found out the temperature gradient is a little more complicated. Depends upon the physics, whether it's radiative or whether it's convective or semi-convective. So we're going to finish that today. We're going to find out that it depends upon the mean opacity of the transfer of photons. I mean, let's think about that. Temperature gradient, adiabatic is the motion of cells. We talked about that last time. I showed you how you derive the adiabatic gradient. But now we're going to talk about the radiative gradient. Well, obviously, if the temperature gradient depends upon how photons are propagating, we have to talk about radiative transfer. We have to talk about the opacity of the material coming through and the optical depth. So our goal today is going to be, let's talk about the connection between radiative transfer and the radiative gradient. And that's going to be very, very skimming the surface discussion of that connection. But you're going to see where the radiative transfer comes into being, okay, in that gradient. In other words, you can't solve that gradient without knowing what the opacity is like. And then when we come back, we're going to say, okay, let's look at how that opacity changes with depth in the atmosphere. And we're going to put it all together. And believe it or not, we're going to come up with a nice closed formula for how the temperature changes as you go down in the atmosphere. It's a very simple formula so that actually you're not going to be using anything complicated. All right. The hard part, we're going to find a very simple formula for how the temperature changes with depth. Then the hard part becomes calculating the pressure at each depth. So that it's not like you have to deal with the temperature and the pressure as a function of depth in your atmosphere, because I'm going to actually give you a formula for the temperature, which is based upon some assumptions of radiative transfer, okay? But under that assumption, then all you'll have left to do is calculate the pressure of each layer. And once you know the pressure at each layer, that tells you the total N. You set this mechanism into motion, solve for that layer, and then you apply the pressure gradient minus g rho to get to the next layer, and you just kind of step down the atmosphere. Okay. So my quest now is, let's talk about the temperature gradient in terms of the radiative gradient. And today I actually want to introduce to you the superadiabatic gradient, but I am not going to spend 2 hours deriving the mixing length model, which I've done in the past, and students said, you could probably let that go and just point us to the notes if we want to look at it later, and here's what the answer is. So I'm going to go with that method this time. And then we'll go to the radiative transfer and figure out how to get this temperature as a function of depth equation. Okay? And I have a whole write-up on the stellar model that says, here's the steps, this is what you do, this is how you iterate it. I'm a lot nicer than my professor was back in 1989. So if you don't think I don't understand your pain, I understand your pain. I know what it's like to go through grad school and have this stuff thrown at you, and what it's like to go back into my office later and pound my head against my computer for hours in a blackboard. So
I'm just surprised you guys had computers back then.
Well, I have to admit, they were terminals about that big, and they were green on a black background with no color.
I think it
was like 1991 or 2 that we had the first X terms, and it was slow as molasses. You call up a window, and then you would just, the window would come on, you know. And it was all black and white. I've seen some major transformations in my time. Okay. So let's go back to our handy dandy notes on the temperature gradient. All right. Let me remind you of a couple things. Can I erase this now?
Yeah. Which page are we starting with, so I know where I am? Because there's like several pages.
I'm starting on this page right here, which has the adiabatic gradient on it, because I just want to remind us of that before we move on. Okay. Thanks for asking. I also forgot to tell you something about the homework. You should see there's a website link at the top of the homework. It says /atomic data. You go there and there's some tables. What I've done is I've put some tables of partition functions, log partition functions. So you have to unlog them, okay, unless you do the log version of SAHA. So they have the partition functions for all those different elements for as a function of temperature, and you just basically have to read off the right one, put it in your code, and you might have to interpolate along that function as a function of temperature. Okay, and I also give the atomic mass units, I give the ionization potentials. I think it's all there, okay, so that you can pluck them off. I believe I have ionization potentials. All right, we came up with a general expression for the temperature gradient, dt dr, and I put an x down here, meaning that actually the slope of this temperature is a function of radius, depends upon the physical processing that's transferring the energy. So we came up with a very general formula, and I believe there was a beta here as well that I don't have in my notes. My apologies, I do have that beta in my notes that are in the typewritten notes. And then we had this gradient, and the gradient I believe was defined as dln of t over dln of p, so that's t over dt times dp over p, where the equation you're deriving here is the equation of state, okay, and that was basically, the equation of state was p equals k u m a m u times rho beta t, I believe. Okay, I believe that was a beta.
M is just like the atomic mass unit.
It's the atomic
It's
mass
not
unit.
the gas, it's just...
Right, AMU is the atomic mass unit of the gas, because what you're doing is you're multiplying that standard mass number by the mean molecular weight
To get it in grams.
to get it into grams, right?
Just check.
Right. Okay. So the slope that this was, if you remember, I drew a graph of ln of p versus ln of t. The slope of that is basically the gradient, and it depends upon the way energy is transferred. At any given t in rho, we know what the p is, or at given p in rho, we know what the t is. We know how these vary because we had that equation, d rho over rho equaled alpha, you know, whatever it was, dp over p plus minus delta dt over t plus phi of d mu over mu, or something like that. So we had that relation. Okay. So anyway, when we looked at the adiabatic gradient, okay, if you remember, you basically took this derivative for constant entropy. Remember, entropy was dq over t. Constant entropy means that dq is unchanging, okay? And dq was the total heat content, all right? Which is kinetic energy plus work potential. And we got 1 minus 1 over beta squared times 1 minus beta times 4 plus beta.
Should be plus 1 over beta squared.
Thank you. Over 1 over 5 halves, isn't it?
Yes.
Plus 4 over beta squared 1 minus beta. Anybody remember what beta was?
Like 1 minus gamma over gamma, maybe? Nope, just
I love it. That was awesome. This is the ratio of the gas pressure to the total pressure, which is the ratio of the P gas over P gas plus P radiation. Okay. P gas was N nuclei plus Ne times KT, or if you want to put some rows in there and some mu's, you're more than welcome to. And then anybody? It's 1/3 AT to the 4th for the radiation pressure. Okay. All right. So this kind of is our main big dog. And we said that you take that under constant entropy such that you hold dq constant. That forces a relationship between the work. Basically means the negative of the work equals the increase of the kinetic energy, or the vice versa. That would be adiabatic. And you get, for that gradient, this function of beta. Okay? And we talked about what happens if you are in a radiationless gas and whatnot. Okay? So, what about if you're doing radiation instead? Adiabatic, remember, is a cell of material, rises up, does work, the kinetic energy decreases in proportion to the negative of the work. Boom. Okay. No energy is lost to the element. It's just exchanged from work to kinetic energy to work. Okay. Okay. Now we want to let the radiation be transferred via photons. Well, up here at the beginning of this set of notes, it's the old equation that we talked about. Tau equals the opacity times ds, and that gives the optical depth is equal to the integral of the opacity over the path length, or standard radiative transfer. Okay, and then we talked about how the optical depth was really the number of mean free paths that the photon goes through the gas. So we ended up having that the mean free path of a photon was 1 over the opacity. Okay. Now, there's something that is missing a little bit from my notes, and that is that this is at a given frequency. Okay. So the mean free path of certain photons is longer than the mean free path of other photons. So we have a very, very complicated problem now, where some high energy photons might travel far before they deposit energy into the gas, and other photons of lower energy might travel less far, or vice versa. And then how do you account for that? Okay. Well, I'm going to introduce to you something called the mass absorption coefficient now, because the formalism of all of this material in the literature for the last 40 years, that you'll read it if you go back and read it, uses the mass absorption coefficient, not the opacity. Remember, the opacity is in units of centimeter minus 1. Okay, so it is literally the inverse of the mean free path. What other people use is something known as kappa. Okay, and kappa is known as the mass absorption coefficient. All right, and it basically is equal to rho times chi. Nope, I've got that backwards. Excuse me, pardon me. Kappa is defined that if you multiply it by rho, it returns to you chi. My bad. Chi is in units of centimeter minus 1. Rho, centimeter minus 3. Right? So what is kappa? What? I missed something. Rho is in units of grams centimeter 3 minus 3. Right. So what does kappa have to be to get out centimeters?
We all know what you meant, Jody.
It's a rough day.
More gammas?
Yep. Just on my brain.
Centimeter squared per gram. So they call it the mass absorption coefficient. I like to think of it as the cross-section per unit mass. Centimeter squared is cross-section per unit mass. Okay? It's frequency dependent. Okay? So that means we can write the mean free path now as 1 over rho kappa nu. As the density goes up, the mean free path goes down. Okay. Now, I prefer chi. Everything I do when I'm doing math and I'm doing this stuff, I always use chi until I'm forced not to. Okay? And then when I'm forced not to, is usually when I have to look up the opacity from an opacity table for a given rho and temperature and composition. I look up my opacity and the gas at that point, and then I have to, and actually they're giving that opacity as the absorption mass coefficient. So I have to multiply it by rho to get it back to chi, and I'm happy again. Okay? Problem is, what is if you don't know rho yet? That's anyway, let's talk about, okay. Now, you'll see an equation over here, which I really don't want to get into yet. What really, to do an average gradient and not solve the big complex problem, we have to average out the frequency dependence in order just to sort of make progress in a way that makes sense. So what we're going to do is we're going to find what's called the gray temperature gradient. Gray is a term used in stellar atmospheres and in radiative transfer, meaning that you're using an average opacity over all frequencies. Okay? Your opacity might be very, very peaked. Okay? It might look like, here's nu, and here's chi of nu, and it might look something like this. Okay? It might really look like something like this. This might be some ionization edge with some other edges from metal lines. This might be like the Lyman alpha, cross section coming in. What we're doing is we're going to find some function which is the average of all that. Okay? It's called the gray opacity. And there are ways to do it. I'm not going to go through this, but it turns out that this is a u sub r, if you take the energy in the gas, the derivative of the energy in the gas per temperature, and weight it by 1 over the mass coefficient, okay, this is one way that you can integrate over all frequencies and come up with some mean inverse kappa.
How is that different than the Rosalind mean opacity?
That actually is the Rosalind mean opacity that I'm not writing. But there are other methods too. Okay, there's flux weighting. And this is actually an inverse weighting because you're weighting the inverse of the opacity, and you're weighting it by how fast the energy changes with temperature. So you're including some of that physics. But there's other ways to also find mean opacities. But you'll find that people adopt the Rosalind mean as the gold standard. And in fact, when you do your stellar model, you'll have to be looking up opacity tables. Guess what? They're Rosalind mean opacities. Okay. But I didn't want to go into deriving the Rosalind mean. If we have time later when we're doing radiative transfer, I can go into that a little bit. Okay. All right, so how do we deal with this? What we want to know is how does the temperature change as a function of radius or distance or propagation length. So it turns out that you can write the flux coming out of some volume as minus 1/3 c times the path length times the gradient of the energy density in the gas. U is the energy density of the gas, and I believe it's equal to a t to the 4th. Use of R. That's the radiation energy density of the gas. Okay, and that's for a black body. If you take a black body and you say, okay, this is the energy distribution, this is the photon density distribution, which you're used to seeing, and then you transfer that to an energy distribution as a function of frequency, and then you integrate over all frequencies at that temperature, you get the energy content is AT to the 4th. Okay. Now what are we basically saying? This is basically the velocity of the propagation times the path length it travels over, and then the change in the energy that happens over that path length. Okay? And that gives you, in a sense, and the third is just allowing for the 3 degrees of freedom, x, y, and z. And they're saying that the flux is decreasing as the energy propagates out in these 3 directions, and this is the rate at which the energy is changing. That gives you the connection between the flux. All right. So if you just do radial, this R is not radial, that's rad. Okay. It's a radiation. Okay. Okay. So if you just do one degree, one direction, this gradient can be written as du dr. All right, but you can write du dr as du dt, which you can take the derivative of that times dt dr, and now we have what we're looking for, dt dr, coming into our equation. Okay, so when you do that, and we're going to take the mean, the Rosalind mean, if you will, of this. So basically, instead of L nu here, we're going to put L bar, where L bar is equal to 1 over rho kappa. I'm going to drop the nu because this is going to be our Rosalind mean. Okay. All right. So we get that the flux then can be written as minus 4 AC over 3. There's the 3. The 4A comes from taking the derivative, 4A, okay? And then we have a t third left over from the derivative, 4AT the third, okay? And then the mean path length is rho kappa, 1 over rho kappa, and then dt dr is tacked on to the end.
C is the speed of light, right?
C is the speed of light. Right, so this is the speed, mean free path, and then the gradient at which energy changes over that mean free path. Okay. Okay. So if we know the flux, we can calculate this. We can calculate dt dr. So what I'm going to do now is I'm going to write going to solve this equation for dT/dr because that's what we want. Okay. So dT/dr is equal to minus 3 rho kappa over 4 AC times the flux over T to the third power. Okay. Now we're going to apply something that's done in the literature all the time. And that is we're going to apply a principle that no matter where we are in radius, this is a function of radius, if you will, that this flux is not a function of radius, actually. Flux is conserved at all layers in the stars. If you have a star, here's the surface, and it has a flux coming out of the surface, okay? Well, if you draw a sphere inside there, guess what? The flux coming through that sphere is the same flux as the flux coming through the surface. It has to be. Flux is conserved. Okay? Otherwise, you would have a buildup of energy in a ring at that layer. Or you would have a sink of energy if flux wasn't conserved. So the flux is conserved. So that means the flux at any radius is equal to the flux that comes out of the surface. What's the flux that comes out of the surface? If you remember right, because you've taught this in 110 a billion times by now, I hope, or at least once for some of you, that when you take the black body curve over the surface at any given temperature, the flux, the energy coming out per unit centimeter per unit time, turns out to just depend upon sigma times T to the fourth. Why did I put an effective there? Okay.
Because it's not the same as the temperature of our layer.
Well, stars have what are called an effective temperature at the surface because they don't have a surface. And whenever you collect light, it's coming from this gas that changes temperature with depth, and the photons, some are coming from lower depths, and some of the photons you measure are coming from higher depths. So you average all that, in a sense, and you get an effective temperature. The actual definition of the effective temperature is that it's the layer of this atmosphere in which tau equals 2/3. Okay? We'll get into that later, but that's the definition of T effective. Okay? It's the temperature of the surface, quote unquote, where the optical depth is 2/3, so that your escape probability of your photons is e to the minus 2/3. Or not escape probability, but your escaping photon ratio. Okay, given that knowledge, dT/dr is equal to minus 3 rho kappa 4AC times sigma T effective to the fourth over T cubed. Okay. All right. Now, that's this equation right here. This invoking line here should have a beta in it, which when I wrote these notes is before I included radiation in the gas. But the point is that you can solve for rho from the equation of state over here. Okay? Basically solve this for rho and substitute it into this equation. And what do you get? You get minus, oh, there's also one more thing. A, that constant A, you can also show from the black body that this is equal to 4 sigma over C. That's actually the definition of A, okay? And so doing that, you get 3 kappa times the pressure over 16 times mu m sub a mu over k, this is the Boltzmann constant, times, there's a beta in here, and then times T effective over T to the fourth. Okay, this was T thirds, T to the 3, now it's T to the fourth. That extra power of T came from solving for rho here out of the equation of state. That means it should be a 1 over beta, shouldn't it? P. Indeed, if you're going to put the beta in there, it should be a 1 over beta. As far as I can see. Anything that's on the bottom over here ended up on the top over there. Anything on the top over here ended up on the bottom over there. So yes. Okay. Now,
I mean, maybe I'm not looking at it right, but I think it's on top in the text written.
yeah, I think it is on the text. Maybe I've got this on the wrong side here.
Yes, I think that's supposed to be 1 over.
That's funny because algebraically this is telling me it's on the bottom, but I do know that it's supposed to be on the top. Okay, so apologies for that little glitch in our algebra today. It shouldn't detract us from what we're getting at here. All right. Here's the last step. This is the radiative gradient. Okay? X equals R. If we now look at this form of it, which is our general derived form, we can now solve for the radiative gradient del. Okay? And when you do that, you get the final solution down here, that del radiative, okay, is 3 over 16 kappa p over g. And where does my beta go? It goes in,
Oh yeah, yeah.
oh, I guess the beta drops out.
Yeah, no, it's not there. Okay, so now this is your general form. This is your general form. And if you're adiabatic, which we describe what that means, this is how you calculate that. If you know your gas pressure and your pressure, then the energy conservation of work equals minus kinetic energy change gives you this relationship for how temperature changes as the gas cells go up or go down. Now if you're talking about radiation and you're talking about how much the energy in the gas changes as a function of radius over the mean free path that a photon travels, okay, you end up with that as the gradient. It depends, it's linearly proportional to the opacity. That should make sense. Large opacity means short mean free path. Short mean free path means energy is getting transferred over short scales. So your gradient is going to be steep. Temperature is going to change very rapidly. Okay. Depends upon the pressure, inversely proportional to the mass over the radius square of the star, and inversely proportional to the temperature, to the fourth power, very strong. Okay? So you basically now have this relationship so that if the star is transferring radiation
strictly by energy via radiation, it goes as this gradient. Okay, and you notice that the G's cancel out and whatnot. Okay, and if it's adiabatic, it goes as that gradient. I guess we didn't get to the other notes today.
Not to continue to be that person.
Please be that person, because this helps me correct many of my notes.
Okay, but is there a cubed here or
No.
no? Okay.
Okay, so this is a typo.
Okay.
Good catch, thank you. So equation 8.48, T affected over T cubed, quantity to the fourth? Not so much. Okay. All right. Okay. So, what I need to emphasize again before we move to the next stage is radiative gradient depends upon how the photons, on average over frequencies, interact with the gas. A true full-blown solution will have to solve these equations at every frequency simultaneously. Okay, I have given you a very averaged solution that's integrated over all frequencies, so you only have to solve one equation as a function of radius. Okay? And I know you guys are burned out, but this is my only opportunity in the next 10 minutes, which we have 7 minutes, so in the next 7 minutes, to talk to you about the superadiabatic gradient. Something that you will not have to use in your model. In fact, you don't even have to use the convective gradient. Okay? You're actually going to be using the assumption of a radiative gradient in your model once we get things settled up. But let's look at the notes for the next few pages, just to look at them. I just want to educate you on them so that if you ever are interested in this, you know what to do. Okay. All right. First of all, this first page about breakdown of this diffusion approximation. There's a paper here you can read. Basically talks about a simple equation where you can multiply the radiative gradient by another function. It's called R sub d. That allows you to account for the breakdown in what's called the basically the Roslin mean opacity. Okay, and assuming this equation here assumes something we call the diffusion approximation that I didn't get into, but it basically assumes that the mean free paths are pretty short. When the mean free paths become very, very long, such as toward the top of the atmosphere where photons start to actually escape space, this breaks down. So as you get toward the surface layer of the star, this breaks down. And this little function R sub d, which is known as the Hop function, Q of tau, we'll talk about that later. We will talk about this Hop function later. Is one way that you can do that. So I just want to introduce to you that, and later I will show you what the Hop function is, and then you can say, oh, well, if I want to account for the breakdown in the diffusion approximation, I can use this equation, multiply it by my gradient. Okay? All right. So you will see in my notes RD times gradient of R. Okay? So in the diffusion approximation area, RD is just 1. Okay. All right. So there's a lot of math in the next pages, but they all center around this simple picture of an element with the surrounding pressure. Okay. It has an sub E. It's an element. It has a given temperature, pressure, and density. Okay. The assumption that we're going to make always is that the pressure surrounding the element is the same as the pressure in the element. The pressure, the element will rise, its density will decrease, its pressure will decrease, its temperature will decrease. Okay? The temperature decreases in proportion to how much work was done, This we're assuming constant entropy.
Wouldn't the
that-
density decrease?
The density would decrease as well. Yes. Okay, so all those deltas are negative. Delta P, delta T, as it goes up. And so the bubble is bigger now. It's in an environment that has lower pressure, so it expands into it. The density goes down, temperature goes down. The work it did to expand is the inverse of the temperature or the kinetic energy. Okay. So what you want to know now to understand this energy transfer is you want to know how much work the bubble did, and you want to know whether the force acting on it, the buoyancy, is positive or not. Because if it's positive, then the gas is unstable to having rising bubbles. Okay. In the end, there's a lot of mathematics here which get you to something called the Schwarzschild criterion. Okay? And this is basically a relationship between the two gradients. The adiabatic gradient is less than the radiative gradient, then that's a condition for dynamic instability, convection. In other words, if the temperature due to adiabatic convection, if that slope is shallower than the slope from radiation, you'll be unstable to convection because energy wants to transfer it the most efficient way. The real Schwarzschild criterion is given by when the adiabatic gradient is greater than the radiative gradient, you're stable against convection. In other words, you will have a radiative transfer. Okay? So you can go through my notes if you want to see how that's derived or not. Okay? Just so you know, I have a graphical picture of that here at the bottom of this page, which I don't have time to really go into the intuition of. Okay? But I just wanted to introduce it to you, that when the lines are in this proportion for the density, but this is the actual Schwarzschild condition, when the radiative gradient is steeper than the adiabatic gradient, you're unstable to convection. You're going to have convection. Okay? Now, there is this thing called the mixing length model. I have probably a dozen pages deriving how do you calculate the temperature gradient when you don't have a perfect adiabatic convection, but you have some inefficiency in the convection. Okay. What did we say the adiabatic was? I'm gonna draw this to a head quickly, so don't think we're gonna be here 15 minutes. What did we say the adiabatic process was? From the picture we saw, the gas cell rises. It does work to expand. The energy content drops in reverse proportion to the work done. There's no energy lost to the element. It did work. Its internal energy goes down in direct proportion to the work it did. There's no energy lost to the environment. But in reality, when a bubble rises, some radiation is also leaking out of the bubble. You see where it gets complicated now? And it depends on, well, how optically thick is the bubble? What's the efficiency? How much radiation gets lost as a function of how much height got raised, or how much energy it lost, or how much work it did. That's what these 12 pages of equations do. They figure out the physics for that. Okay? I'm not going to go through that with you, but if you skip ahead, I will show you the page where it shows you the formula on how to calculate what that final gradient is. Oh my gosh, look at all these pages. All right? And here it is. It's right here. It's called Mixing Length Model, the Solution. Kind of like Spaceballs, the t-shirt. Hey, you guys are like, I'm so done with this. Spaceballs, the toilet paper. All right. Anyway, putting it all together, you have two equations. In this first equation, One is basically energy transfer. The other one is basically efficiency conservation of the flux. A is equal to all of this stuff here, and B is equal to all of this stuff here. Okay, so you can calculate those. Those are actual state variables local to the gas. Okay, you can solve then down here and turn this into a, what is it called? Cubic equation. Get out your handy dandy Brent, solve your cubic equation. Well, it turns out that this one has two imaginary roots and one real root. One real root, we solve for that. That real root we're going to call x naught when you solve this equation for the zero. And then once you solve for x naught, you can back substitute to get the true gradient in terms of the adiabatic gradient, B, and the solution to this equation. And you can get the gradient in the element as the true gradient minus the solution squared. And you come up with basically this del with no subscript. That's the one we're after. That gives you the true gradient when you account for inefficient, when you account for the fact that radiation is escaping the bubble as it rises. It's complicated, you know? It didn't take me a half hour to write those notes down. It took me literally, you know, a couple months of studying a bunch of different papers and finally having the light bulb go on and then trying to synthesize it. So that was a lot of work, but for me it was very rewarding because now I think I really truly understand the superadiabatic gradient. The point is, if you're in perfect convection, you use this. If you're in perfect radiation transfer, you use this. And calculate A and B. You solve these equations down here. You get the solution for if you are in the real situation where some radiation is being emitted. Okay? And there you notice the heat capacity. C sub P is there. The scale height. Okay? Then there are some other things like delta. Remember delta that appeared in our differential equation for the density? It was minus delta dt over t, that term. The delta shows up. So there's a lot of physics in here that goes into this. And there's an assumed optical depth for the element, which depends upon the opacity, the scale height, and the density, etc., etc., etc. So anyway, the thing is, you don't have to understand all that physics. If someday you decide you want to be able to make this calculation, you can just go to these notes. Or you could go to these notes, which are actually, I think, better than the handwritten notes. And it gives you the equations. And in fact, it turns out on the next page, I give how you solve for x naught. Or at least I think I do in these notes. It turns out you can solve x naught analytically. So it's not that hard, actually. Maybe hard to understand all the physics and assumptions. Not that hard to solve. Thank you for your extra few minutes today. I do appreciate them. And when we get back, we'll start the radiative transfer so we can get the function of the temperature as a function of distance.